And next up, we have Jacob Garcia from University of California, Riverside, who will be telling us about stability and the Morse boundary.
All right, thank you very much for the introduction and very much for inviting me to the conference. I have been fueled by coffee and Zoom for the vast majority of the day. So it's been a great seeing everyone's talks and hearing what people have to talk about. No. All right, so before I get into it, just a slide on general assumptions. So for this presentation, I'm going to be considering proper geodesic metric spaces as they all should be. And I'm also going to be considering finitely generated groups also as they all should be. So hopefully the people in this audience, these are some very natural assumptions for us to put on some metric spaces and some groups. And hopefully I'm not stepping on any toes by assuming that these things are true. Okay, so I want to start off with some history before I get into what I'm going to be talking about. And so the first bit of history that I'm going to be talking about is the concept of a Kleinian group. Okay. So a Kleinian group is a discrete subgroup of orientation preserving isometries on hyperbolic 3 space. So they were first thought about by Felix Klein, because he was interested in studying surface groups and then generalizing these ideas of surface groups to higher manifolds. One of the reasons that you might be interested in studying Kleinian groups is because every hyperbolic 3 manifold is the quotient of a Kleinian group on that hyperbolic 3 space, right? So this is a collection of groups that have been studied for quite a long time. And more recently than 1883 was the concept of convex co-compactness. So this was parts of this definition were discovered independently by Martin and Sullivan, called convex co-compactness. So we take a Kleinian group and we look at one of the following equivalent conditions. And I'm going to spend some time talking about each of these conditions one at a time, because we're going to be seeing these conditions show up again and again in slightly different variations, but the idea behind these conditions are the same. So if any of you have had the pleasure of meeting Burns-Healy, he has the wonderful advice that every time you see a concept on a group, right, you should be thinking, can I understand what this means for the integers? Okay, so I'm going to be drawing some pictures of the integers as a subgroup of orientation preserving isometries on hyperbolic space, except it's very hard for me to draw hyperbolic 3 space, so I'm just going to be drawing hyperbolic 2 space, but the idea should hopefully be the same. So we have that my group acts co-compactly on the convex hull of its limit set. So if I draw my hyperbolic 2 space as the disk model, right, and I draw some integer orbit point here, where up to me apparently being a good artist, right, they're supposed to appear like they're getting closer and closer, right? The limit set for this group is going to be these 2 points here on the end, right? So here in the blue, that's the limit set of Z, right? And the convex hull of its limit set is just what I normally mean by convex hull. I'm going to connect all of the points on the boundary with geodesics, and then I'm going to connect all of the points on those geodesics with geodesics to all the other points on other geodesics, and I'm going to keep doing this until I don't end anything else. So here, my convex hull is just this line which goes through the orbit. And so what I'm saying is that Z has a co-compact action on this line, right? Which makes sense, right? I just take closed balls that are big enough around the orbit point, and then these just translate left and right on this line. Okay, cool. All right, the second property that we have is that we have a co-compact action on the entirety of H3 union some omega, right, where omega is like the complement of the limit set on the boundary. We call this the domain of discontinuity. So if I draw my same picture again thinking of the integers, right, I had these 2 points, which were my limit set. And now this set that I'm interested in is just everything except for those 2 blue points. Right, so I have both my circle boundary and the entire interior except for these two blue points. And the co-compact set that I'm going to act on is I'm going to take some sort of vertical slice. Actually, this vertical slice should look like it disappears on the boundary. Or maybe not disappears, maybe I should give it some thickness just because it's easier to imagine. So then if I translate this vertical slice left and right, because it's inside, it includes this boundary edge on the top and the bottom, this is going to be a compact set, which translates left and right by z on the side of this set, right? So this is my compact set that my group acts on to give me a co-compact action. And this is very much related to north-south dynamics. If you've ever heard of these, right? I have like an attracting point on one side and a repelling point on the other side, right? And so when I remove those 2 points, I get a nice group action on what remains. Okay, the third condition says that any gamma orbit is quasi-convex, and that just means that the convex hole of my orbit is contained in some epsilon neighborhood of my orbit. So here I have my orbit by integers, and I can think about connecting any 2 points of this orbit with geodesics, and maybe I'll draw them slightly off of the normal geodesics. And all that I'm saying is that there exists some epsilon neighborhood, so that way when I take the epsilon neighborhood of all of my orbit points, well, that epsilon neighborhood around all of my orbit points contains all of my geodesics. And then finally, I have this condition that says that every limit point of my group is conical. So let me tell you what that means. So let me draw a piece of the boundary of my space, right? And I'm going to take a limit point here. So being conical means that if I take any geodesic representative for that point on the boundary, then there exists some K neighborhood, right? So this here is the neighborhood, right? It's the K neighborhood of my geodesic ray alpha, right? No matter what geodesic ray I started with, that geodesic ray will intersect my orbit at least once. And in fact, will intersect infinitely many, because I can always make the ray smaller, and then that will have to intersect again. And then I can make it smaller to remove that intersection point. That has to intersect again, right? So for any geodesic which represents my limit point, there exists some neighborhood, so that way that neighborhood intersects my orbit an infinite number of times. Right? So that's what it means to be conical. The reason that this is called a cone, by the way, is if instead of drawing this in the disk model, if I drew this in the upper half space model, right? So I have everything above this line, then the K neighborhood of a geodesic ray which points to the boundary looks like a 45-degree cone, right? So this distance here, this is K, and this distance here is also K, right? So this K appears to shrink, and I get like an ice cream cone shape pointing down to the boundary. Okay. All right, so again, this story is from the 1980s, but since then we've come up with better definitions of what it means to be hyperbolic, or maybe not better definitions, but different definitions of what it means to be hyperbolic. Right? So we have the concept of what it means to be delta hyperbolic. We have Gromov hyperbolicity, right? I'm sure that, every good geometric group theory talk is supposed to give this definition at least once, right? So here's the definition, but I think that most people have seen this definition. One thing that's going to be important later is that delta hyperbolicity is a quasi-symmetry invariant, right? But again, I imagine that most people here have probably seen this before. Right? Okay, but one thing that we have is that, okay, so H2, since I draw it in the disk model, it has a very obvious boundary, right? It's in a disk, so that means, or it's a ball, and the boundary of the ball is a disk, and H3 is a ball, boundary of that ball is a sphere, and et cetera, et cetera. Yeah. But for an arbitrary delta hyperbolic space, I can define a boundary which is analogous, called the visual boundary. Right. So first, we define what it means for two rays to be asymptotically equivalent. Right. It just means that their Hausdorff distances are bounded. Right. So two rays which are not equivalent are rays which point in different directions. Right. Because as I follow one of these rays out, right, the distance from this point over to this ray gets farther and farther as I move this point farther and farther down the ray. But yes equivalent. So maybe for fun, I should have called this no equivalent, not yes equivalent, right? If I have two rays that appear to travel parallel as they get farther and farther down, that's exactly going to satisfy their Hausdorff distances being bounded. And we should think of like the maximum distance as the distance between the starting points. Okay. So the visual boundary is the set of all asymptotically equivalent rays that all start at a given base point. And there's a standard topology that we put on these rays where we say that 2 points at infinity are close, right, if their geodesic rays fellow travel for a very long time. Right? So if I have my base point x naught, right, here I have 2 points on the boundary. Maybe I should put my points on the boundary a different color so they're easy to see. And I want to say that these 2 points are closer than the point down here. Well, if I draw the rays which go to these points, right, we'll see that the first 2 rays fellow travel for a very long time, right? Whereas this third ray diverges much sooner from the first 2. So this is how we define closeness, and this is how the topology works. Okay. So then we get an equivalence class, which I just denote. If I have a ray alpha, I'll just plug in infinity, and by that I mean the point at infinity or the point on the visual boundary. Okay. And again, if I have a quasi-isometry between 2 hyperbolic spaces, that induces a homeomorphism on their visual boundaries. Okay. So I have this theorem / definition from Martin and Sullivan talking about convex co-compactness in H3, right? And this is talking about relationships between a subgroup of a hyperbolic group and the sphere boundary of H3. And now I have some generalizations of those things, right? I have a hyperbolic space, which isn't H3, and I have a boundary at infinity for that. Right? So I can ask, are there some analogs to these 4 statements in this generalized set? And the answer is yes, right? So in 2001, Eric Swenson showed that the following 5 statements are equivalent. I'm not going to be going through them as carefully as I did the first time. Just note that this first property says that I have a co-compact action on some sort of convex hole of the limit set. My second one is I have a co-compact action on a domain of discontinuity. I have some sort of quasi-convexity inside of my space. I have a conical condition, and I have a horospherical condition. And I'm not going to define what it means to be horospherical, but if you've seen horospheres before, it's exactly what you think it is. Right? And then Swenson defined groups as above as quasi-convex groups. So we do get a generalization to all hyperbolic spaces, not just H3. Okay, so if I can generalize from H3 to any hyperbolic space, well, can I generalize past hyperbolic spaces, right? There's lots and lots of groups that have hyperbolic-like behavior, but are not hyperbolic, right? And we've seen these kinds of spaces in lots of the talks during the conference already, right? Mapping class groups, ket zero groups, relatively hyperbolic groups, outer automorphism free groups, right? So can we extend this idea, right, this classification of groups to these other spaces, right? So the first thing that you might try is to say, hey, I can construct a visual boundary on whatever metric space I want, right? And I can also just see if a group has a quasi-convex orbit embedding. But unfortunately, these 2 things are not invariants under quasi-isometries for non-hyperbolic spaces. Okay? So we need to come up with a different kind of boundary, and we need to come up with a different characterization for my. Okay? So so we'll start with the boundary, right? Generalized, right? Talking about the boundary generalization. So the first thing that I want to talk about is called the Morse lemma, right? So if I have a delta hyperbolic space, then any KC quasi-geodesic has to stay close to a geodesic between its endpoints. Right? This is an extremely useful lemma, right? It's actually the main tool that you use to prove, right, that hyperbolicity is a quasi-isometry invariant, because triangles get sent to quasi-triangles, okay? And then those quasi-triangles stay close to the original geodesics because of the Morse lemma, and then the triangles delta hyperbolic. Well, Matt Cordes, in his PhD thesis, realized that, hey, this is an extremely useful lemma. And what we're going to do with this lemma is we're going to kick out the word lemma, and we're going to replace it with the word definition. Okay? It's one of the very nice things that we get to do as mathematicians. If you have something that's a true lemma in a space and you want to use it somewhere where it's not true, kick out the word lemma, replace it with the word definition. Right? And so we have the definition of a Morse geodesic, right? And so if you compare the statement of the Morse lemma and the statement of the definition for being n Morse, all that I'm saying is that a geodesic is n Morse if there's some function n, so that all KC quasi-geodesics, right? So this is a KC quasi-geodesic, stays within n of KC of the original geodesic. Okay, so, right, so using this definition of n Morse, you can define a set called nn of 0, which is, or let's call it x sub 0, which is the set of all x in your space such that the geodesic from x to x0 is n Morse. This is called the Morse strata with respect to the Morse function n. Okay? And you can show that every single one of these Morse strata is a hyperbolic subset of your space. Furthermore, every single point in any proper metric space is eventually in a Morse strata. Okay? So these sets actually form an open cover of your space. Each one is hyperbolic, so they all have their own Gromov visual boundary, right? And we can construct a Morse boundary which is analogous to the visual boundary by taking a direct limit, right? So the Morse boundary is just going to be equal to the limit of all of the visual boundaries of these Morse strata at a point, right? As you make the Morse gauge bigger. Okay? And Cordes showed in 2016 that this is a quasi-isometry invariant for any proper geodesic metric space, which is excellent. Okay, so now we want to talk about a generalization for the group. And from this, we're going to take inspiration from mapping class groups. So Farben-Mosher in 2002 and Kenton-Leininger in 2008, they came up with a generalization of quasi-convex, which they called convex co-compact for mapping class groups. So here I have a weak convex hole condition. Here I have a co-compact with a domain of discontinuity. I have a quasi-convexity condition, and I have a conical condition. But their construction used type Mueller space. So Farben-Mosher in 2002 asked the question, how does their version of convex co-compactness relate to quasi-convexity in the mapping class? Because they have a statement about quasi-convexity in type Mueller space, but they were wondering how does it relate to quasi-convexity when you take the orbit inside of the group instead of the orbit in some space that the group acts on. Right. So this was answered by Durham and Taylor, and later Cordes and Durham in 2015 and 2016 respectively. They defined what it means for a subgroup to be stable. Right. So you need a quasi-symmetric embedding, and everything needs to be contained, or maybe not contained in a Morse strata, but all of the geodesics need to be uniformly Morse. Okay. And this gives us a stronger notion of quasi-convexity. Right. In fact, every stable subgroup is a quasi-convex subgroup. It's a quasi-convex subgroup plus some extra conditions. Right. And then they showed in the setting of mapping class groups, right, that every convex co-compact subgroup in this definition of mapping class group is exactly a stable subgroup of the mapping class group. And stable elements are exactly pseudo and nosobs inside of the mapping class group. Inside of cat zero spaces, the stable subgroups are the ones that all have rank 1 isometries. So it's actually a generalization of a lot of things that people are very interested in these types of spaces. So we have our new candidates. We have a new boundary at infinity called the Morse boundary. We have a new idea for quasi-convexity, which we're going to call stability. Right? Both of these are invariants under quasi-isometry. Right? So these are some good candidates. And some work towards using these two options as generalizations has already been shown. Right? So here was Swenson's original statement. This is what we're trying to generalize. Right? And statement 1 and 3 were already shown to be equivalent by Cordes and Durham in 2016. Right? So here I have a convex co-compact action on a convex hole of my limit set. And I have a generalization for quasi-convexity called stability. So they show that these two conditions were equivalent. So there are some other conditions from the statement left to show, right? So this is what we want to do, and they're numbered the same way. Right? So statements 1 being equivalent to statement 3, that was the Cordes and Durham result from 2016 that I showed on the last slide, right? Showing that 3 is equivalent to 4, that is recent work coming to a thesis near you, right? To be completely fair, Cordes and Durham showed that 3 implies a different variation of 4, but their definition of conical wasn't strong enough to show the converse. So part of my work was to find a slightly stronger definition of conical, which is implied by 3, but also goes back to 4. And I've also shown that there is a definition of 5, so that way 4 implies 5. Right? So still to show, right? So open, which I'll do in the green, is going backwards, right? It's been very difficult to show that 5 implies any of these statements, right? Can you go in any direction from 5 backwards, right? And knowing how 2 interacts with the picture has just been very, very challenging. It turns out that the Morse boundary, right, that the Morse boundary is only a compactification of your space if and only if X was delta hyperbolic to begin with. So it's very hard to construct compact subsets inside of this Morse boundary closure because I don't have that the Morse boundary is a compactification, right? I can construct a closed set the same way that Swenson did, but trying to find a compact set is bigger. All right, so that's what's happened so far with this story. And I think I'm going to go ahead and leave it off there. So thank you very much.
Well, let's thank the speaker. Any questions for the speaker? Okay, I think I have one question. So just right here. So you wrote into some generalization of a domain of discontinuity. Do you have a good candidate for that?
No. So yeah, okay. So there are 2 things that you could try, and we tried both of them, right? Okay. So the domain of discontinuity, right? This omega, it should just be the Morse boundary without the limit set, right? That's what it should be. But acting on this via your subgroup is very hard because even though you have this nice stability condition for your group acting on its orbit, right, it might send points which are out of the orbit outside of a given force strata. Okay? And so it's very nicely behaved around the orbit, but far away from the orbit, the group action we have no control over. And so talking about the domain of discontinuity, right, going back to this picture, right, even though I know that the group behaves nicely around this like quasi-axis, I don't know how the group behaves like up here, right? And that makes it very hard to get arguments to go.
Got it. Okay. And this is one possible. You said there are a couple of possibilities you're thinking, or
yeah. So you could try defining the domain of discontinuity to be like a single Morse strata, or to like try to like restrict yourself to, okay, let's assume that the orbit is contained in the boundary of a specific strata and then try to restrict this, but then your group action isn't well defined anymore because it might send the strata outside, right? So yeah, there's been like some technical details that have been making this tricky so far. So yeah, ideas for what the right statement for number 2 should be has been very difficult.
I see. All right, thank you. Any other questions? Okay, if no, let's thank Jacob again for his talk.